Picture this. You're sitting on your couch, you open Netflix, and within 2 seconds a movie starts playing in HD. Or you send a message to someone on the other side of the world, and it arrives instantly. Or your bank knows, in real time, that a fraudulent charge just appeared on your card. How does any of that actually work? The answer is networking. And once you understand it, the internet stops feeling like magic and starts feeling like an incredibly clever system of tubes, labels, and agreements. Let's break it all down. Here's what we're covering today. We're going to start with the basics, what a network actually is and how computers talk to each other. Then we'll look at the internet itself, how it's structured, how data finds its way from your laptop to a server across the world and back again. We'll cover the World Wide Web. Because yes, the internet and the web are not the same thing, and that confuses a lot of people. Then we'll look at how internet software is organized in layers, like a shipping company. And finally, we'll talk about security, viruses, firewalls, encryption, and why you should never open that email attachment from UPS. By the end of this video, you'll have a real mental model of how the internet works. Not just buzzwords, an actual picture in your head. Let's get into it. A network is just a group of computers connected together so they can share information and resources. That's it. That's the whole idea. Now, networks come in different sizes. The smallest kind is called a PAN, a personal area network. That's short-range stuff, like your wireless headphones connecting to your phone, or your smartwatch talking to your laptop. We're talking a few meters at most. A step up is a LAN, a local area network. This is what connects the computers in a building, like the computers in a school, an office, or your home. When you connect to your home Wi-Fi, you're joining a LAN. Bigger than that is a MAN, a metropolitan area network, which covers a city or region. And the biggest? A WAN, a wide area network. These span entire countries or even continents. The internet itself is basically the world's biggest WAN. Now, there's another way to classify networks. Some are open, their design rules are publicly available, and anyone can use them. Others are proprietary. One company owns the technology and controls who can use it. The internet is an open network. That's a huge deal. It means no single company gets to charge you a toll just to participate. The rules of the road, the protocols, are free for everyone. Here's the thing. If you put 100 computers on a network and they all just start transmitting data at the same time, you get chaos. It's like a room full of people all shouting at once. So networks establish protocols, formal agreements about how communication should work. What format do messages use? Who gets to talk when? How do you handle collisions? Think about a phone call. Before you say anything, there's a mini protocol. The phone rings, someone picks up, they say, "Hello." You say, "Hi, it's Roger." A connection is established. Then you talk. And there's an understood rule that only one person talks at a time. Computers have the same kind of thing, just faster and more precise. One famous protocol is called CSMA-CD, Carrier Sense Multiple Access Collision Detection. This is what Ethernet networks use. Here's what it means in plain English. Before sending, a computer listens to see if the line is quiet. If it is, it starts transmitting. But if two computers start sending at the same time, a collision, they both detect it, stop, wait a random amount of time, and try again. It's like two people reaching for the same doorknob at the same time. You both pull back, pause, then one of you goes first. Wi-Fi networks use a slightly different version, CSMACA, where the CA stands for collision avoidance. Instead of detecting collisions after they happen, wireless devices try to avoid them in the first place. Why? Because in a wireless environment, you can't always hear the other person. Maybe a building is blocking their signal. This is called the hidden terminal problem. So instead of listening for crashes, Wi-Fi devices ask permission before transmitting. Now, a single LAN is useful. But what if you want to connect different networks together? For connecting networks of the same type, you use devices like repeaters, bridges, or switches. A repeater just boosts the signal and passes it along. No intelligence. A bridge is smarter. It looks at the destination address on a message and only passes it across if it needs to go to the other side. A switch is like a bridge with multiple ports. It can connect several network segments and intelligently routes traffic only where it needs to go. But what about connecting networks that are fundamentally different from each other, like a Wi-Fi network and an Ethernet network? For that, you need a router. A router is a special-purpose computer that forwards messages between networks. Every machine in an internet has two addresses: its local address within its own network and its internet address. The router uses a forwarding table to decide where to send each message next. The place where a network connects to the wider internet is called a gateway. Here's a question. When you load a web page, what's actually happening between your computer and the server? The answer involves something called the client/server model. A client is a process that makes requests. A server is a process that fulfills them. Your browser is a client. The web server at Google is the server. Your browser asks for a page. The server sends it. This model is everywhere. Print servers, file servers, email servers, all the same idea. One machine provides a service. Many machines consume it. The other model is peer-to-peer, or P2P. In this model, there's no central server. Every machine is both a client and a server. Think BitTorrent, or early versions of Napster. You share files directly with another person's computer. The collection of peers sharing a single file is sometimes called a swarm. P2P is efficient because the load is spread out. You're not hammering one server. But it's also harder to police, which is why it became the favorite tool for copyright infringement. Modern software isn't just running on one computer. It's distributed, spread across many machines working together. A few flavors you should know. Cluster computing. A group of computers that work tightly together to act like one big, powerful machine. They provide high availability. If one machine dies, others keep running. And load balancing. If one machine is swamped, others take over. Grid computing. More loosely connected. Think of the BOINC project, where millions of home computers donate spare processing power to solve massive scientific problems like protein folding or finding alien signals. Cloud computing. This is the big one today. Huge pools of shared computing resources on the network, available to rent as needed. Amazon's Elastic Compute Cloud, Google Drive, Microsoft Azure, all cloud. The metaphor is borrowed from the electrical grid. Just like factories stopped building their own generators once the power grid existed, companies can stop building their own data centers once the cloud exists. You just plug in and pay for what you use. Okay, now let's talk about the Internet, capital I. The Internet started as a research project in the early 1960s, funded by the U.S. Defense Advanced Research Projects Agency, DARPA. The goal was to build a network that could survive local disasters. Even if part of it was knocked out, traffic would route around the damage. Over decades, it grew from a government project to an academic one to the global commercial beast it is today. The Internet is built from networks operated by Internet Service Providers, ISPs, organized in a hierarchy. Tier 1 ISPs are the backbone. Massive international networks operated by companies in the telecom business. Tier 2 ISPs connect to the backbone and serve regional areas. Access ISPs, or Tier 3, are the ones you actually subscribe to. Your cable company, your phone company, or your university's network. The devices at the end of this chain, your laptop, your phone, your smart TV, are called end systems or hosts. Every device on the Internet needs a unique address. These are called IP addresses. Originally, IP addresses were 32 bits long, written in dotted decimal notation like 192.168.1.1. But we're running out of those. The new version, IPv6, uses 128-bit addresses and is being rolled out now. But numeric addresses are hard for humans to remember. So the Internet also has a domain name system, DNS, a massive directory that translates human-friendly names like Google.com into IP addresses. The process of looking up that translation is called a DNS lookup. Domain names are organized hierarchically. The part after the last dot is the top-level domain, TLD, .com, .edu, .gov, .org, .ca, and so on. Before that is the organization's domain. Before that are subdomains. So server1.selling.ebay.com tells you the computer is named server1, in the selling subdomain, in the eBay domain, in the commercial TLD. Neat. Here's something that trips people up. The Internet and the World Wide Web are not the same thing. The Internet is the infrastructure, the physical cables, routers, and protocols that connect machines around the world. The World Wide Web is a specific application that runs on top of the Internet. It was invented by Tim Berners-Lee in 1989 to 1990 as a way to link documents using hypertext, text that contains links to other text. The web uses HTTP, Hypertext Transfer Protocol, to transfer documents between a browser, the client, and a web server. Every document on the web has a unique address called a URL, Uniform Resource Locator. A URL like http://eagle.mu.edu, authors, Shakespeare Julius _Caesar.html, tells the browser, use HTTP, contact the server at eagle.mu.edu, navigate to the folder, authors/Shakespeare/ and retrieve the file Julius_Caesar.html. Web documents are written in HTML, hypertext markup language. HTML uses tags, special symbols like H1, P, and A to tell the browser how to format and display content. The A tag is the anchor tag. It's how hyperlinks work. You wrap text in an anchor tag, point its href attribute at another URL, and boom, that word becomes clickable. HTML's sibling, XML, extensible markup language, is more about meaning than appearance. Where HTML says, display this as a heading, XML can say, this is an ingredient, or this is a price. That semantic richness is what makes things like search engines smarter. When you send a message across the Internet, the software that handles it is organized into 4 layers. Think of it like mailing a package. Layer 1, application. Layer, this is your app, your browser, your email client, your video game. It prepares the message and hands it off. Layer 2, transport layer. This layer chops your message into small pieces called packets, numbers them so they can be reassembled, and hands them to the network layer. The main protocol here is TCP, Transmission Control Protocol. TCP is like registered mail. It confirms every packet arrived and resends anything that got lost. There's also UDP, User Datagram Protocol. More like a postcard. Faster, but no guarantee of delivery. Great for streaming video or voice calls where a missing packet is better handled by just skipping a frame than waiting for a resend. Layer 3, Network Layer. This layer decides where each packet goes next. It uses the IP protocol and each router's forwarding table to route packets toward their destination, one hop at a time. Layer 4, Link Layer. This layer handles the actual physical transmission, turning bits into signals, whether that's Ethernet, Wi-Fi, or fiber optic. At the destination, these layers work in reverse. The link layer receives the signal, the network layer checks the address, the transport layer reassembles the packets in order, and the application layer delivers the complete message. Enough theory. Let's see some examples of how this actually works. Example 1. What happens when you load a web page? Let's trace exactly what happens when you type www.google.com and hit Enter. 1. Your browser, application layer, needs Google's IP address. It sends a DNS lookup request, basically asking, hey, what's the IP for Google.com? 2. A name server responds with the IP address, say 142.250.80.46. 3. Your browser opens a connection to that IP address. The transport layer uses TCP to establish this connection. It's a brief handshake. Can we talk? Yes? Ready? Great. 4. Your browser sends an HTTP request. Please send me your homepage. 5. Google's web server sends back the HTML code for the homepage. 6. Your browser reads the HTML tags and renders the page. Titles, paragraphs, images, links. 7. Each image in the page triggers a separate HTTP request to fetch that image file. All of that happens in under a second. Wild, right? Example 2. Email and SMTP. Email feels old-fashioned, but the protocol behind it is a great example of how internet communication works. When you send an email from dalek@evil.gov to doctor@tardis.edu, here's what happens. Your mail server contacts the mail server at tardis.edu. They have a little conversation using SMTP, Simple Mail Transfer Protocol. The conversation literally looks like, Server A. Hello, I'm mail.evil.gov. Server B. Hello, pleased to meet you. Server A. I have mail from dalekj@evil.gov. Server B. OK. Server A for rcptdoctor@tardis.net. Server B. OK. Server A. Here's the data and sends the message body. Server B. Message accepted for delivery. Server A. Quit. Server B. Goodbye. That's an actual protocol conversation. Each line has a precise meaning defined by the SMTP standard. This kind of formal handshake is what makes it possible for email servers built by completely different companies to talk to each other reliably. Example 3. TCP versus UDP. When to use which? Let's say you're downloading a legal document. You need every single byte to arrive correctly. If even one byte is wrong, the document is corrupted. So you use TCP. It checks, retransmits, confirms. Reliable. Worth the small overhead. Now, let's say you're on a Zoom call. A video frame that arrives late is worse than useless. It messes up the real-time flow. Better to just drop it and keep going. So video calls use UDP. No waiting for resends. Just keep the data flowing. Same principle. DNS lookups use UDP because they're tiny and fast, and if you don't get a response, you just ask again. Email uses TCP because losing part of a message is unacceptable. Example 4. Public key encryption. The digital lock and key. Here's how HTTPS keeps your bank password safe. Normal encryption. You and your bank share a secret key. Problem. How do you share that key without someone intercepting it? Public key encryption solves this cleverly. Your bank generates two keys. A public key it shares with everyone, and a private key it keeps secret. Anyone can use the public key to encrypt a message, but only the private key can decrypt it. So when you connect to your bank, your browser receives the bank's public key. You encrypt your data with it. Even if someone intercepts the encrypted message, they can't read it. Only the bank's private key can unlock it. This also enables digital signatures. If the bank encrypts something with its private key, you can decrypt it with the public key. And since only the bank has the private key, you know the message genuinely came from the bank. That's authentication. HTTPS uses this system through a protocol called SSL/TLS. That little padlock in your browser, it means all of this is happening right now. A virus hides inside an existing program. When you run the program, the virus runs too and tries to copy itself into other programs. Some are just annoying, some destroy data. A worm is different. It travels on its own through a network, no host program needed. It replicates across machines and can flood entire networks with copies of itself. A Trojan horse looks like something useful, a fun game, a useful tool, but it secretly does something harmful once installed. Most Trojan horses arrive as email attachments. Spyware sits quietly on your machine, watching what you type and reporting it back. Passwords, credit card numbers, browsing habits. And phishing isn't malware at all. It's social engineering. You get an email that looks like it's from your bank asking you to confirm your details. You fill in the form. You just handed your credentials to a criminal. The defense against all of this: firewalls, which filter traffic in and out; antivirus software, which scans for known threats; and plain old healthy skepticism. Let's bring it home. A network is computers connected together to share information. Networks range from tiny PANs to the global internet, the biggest WAN of all. Protocols are the rules that make communication possible. CSMA/CD for Ethernet, CSMA/CA for Wi-Fi. Without agreed-upon rules, the network is just noise. The Internet uses a hierarchy of ISPs, from backbone providers down to your local access, ISP. Every device gets a unique IP address, and DNS translates human-readable names into those addresses. The World Wide Web is an application layer on top of the Internet. Documents connected by hyperlinks, encoded in HTML, transferred via HTTP. Data travels through 4 software layers: application, transport, network, and link. The transport layer turns messages into packets. TCP ensures reliable delivery. And the network layer routes each packet hop by hop toward its destination. And security is a constant arms race. Encryption, especially public key encryption, keeps data private. Firewalls block unauthorized access. And staying alert to phishing keeps the biggest vulnerability in any network, the human using it, a little safer. In the next video, we'll dive into databases. How massive amounts of data are stored, organized, and retrieved at scale. From the tables inside a relational database to the queries that pull exactly what you need in milliseconds, it's another layer of the system working invisibly behind every app you use. See you there.